For nearly 2,000 years, it has been sitting in plain sight, at the bottom of harbors, along ancient coastlines, beneath the Mediterranean Sea, structures built by Roman engineers, so long ago that the civilization that made them has been dead for 15 centuries. And yet there they stand, solid, intact, still holding their shape against the constant pressure of tides and waves and the slow grinding force of the sea, while the modern concrete seawalls built to replace them have crumbled. The ancient structures outlast modern ones built to outlast them. This is not a minor engineering footnote. This is one of the most embarrassing gaps in the history of materials science. A civilization that ended 1,500 years ago is producing a building material that outperforms the best concrete modern engineering can manufacture. For most of the 20th century, mainstream science simply assumed that this could not be true. Not examined and rejected, not tested and disproven. Simply assumed, with the quiet confidence of a field that had already decided what the ancient world was capable of. Modern Portland cement concrete, the foundation of virtually every structure built on Earth today, begins to degrade within decades when exposed to seawater. The chemical reaction between seawater and the calcium silicate hydrotite that gives Portland cement its strength breaks down the molecular structure, cracks it, weakens it, fails it. Coastal structures built with modern concrete require constant maintenance, regular replacement, ongoing engineering intervention just to remain functional. For all our technological sophistication, we have not solved the problem of building permanent structures in marine environments. The Romans solved it 1,000 years ago. The Romans solved it 2,000 years ago, not approximately, not adequately. Solved it so completely that their solution is still outperforming the modern engineering industry's best available alternative at 2,000 years later. That is not a coincidence. That is a technology. Roman marine concrete, opus cementitium, was made from a mixture of volcanic ash called pozzolana, lime, and seawater, poured around a framework of rock and rubbed left to set. Simple ingredients, simple process. What happened next is what mainstream science has spent decades refusing to believe. Instead of degrading and exposed to seawater, the Roman concrete got stronger. The chemical interaction between the seawater and the specific minerals in the volcanic ash produced, over time, a crystalline mineral structure that grew inside the concrete, reinforcing it from within, a luminous tobermorite. A crystalline mineral structure that grew inside the Roman concrete as it was exposed to seawater, like microscopic rubber generated by the material itself, not added externally, not engineered in after the fact, produced by the concrete's own chemistry in response to the sea. The longer the concrete was exposed to seawater, the more of this reinforcing structure it developed. The more it developed, the stronger it became. A building material that responds to the shock not by degrading, but by adapting, growing more resilient with every year of exposure. This is the precise opposite of what modern concrete does in the same conditions. Portland cement meets seawater and begins to fail. Roman concrete meets seawater and begins to improve. Two materials, same environment, completely opposite responses. One of them is 2,000 years old, and it is the better one. A team of researchers from the University of California, Berkeley, led by materials scientist Marie Jackson, spent years analyzing samples of 2,000-year-old Roman marine concrete taken from ancient harbor structures across the Mediterranean. What they found at the molecular level stopped them. They were looking at a concrete that had been chemically improving for 2,000 years. Its internal crystal structure, more developed, more complex, more mechanically effective than when it was first poured. Its compressive strength, its resistance to fracture, its ability to withstand wave action, all exceeding modern Portland cement, not approximately superior. Measurably superior, numbers, data, peer-reviewed results. A remarkably durable building material that was, in several important respects, superior to anything available today. Jackson published her findings. The results generated significant media attention. And then the field did what it typically does with findings too inconvenient to absorb. It acknowledged the research, filed it under interesting, and continued pouring Portland cement. The same pattern, the same institutional resistance. A finding too significant to dismiss on too inconvenient to embrace. Sitting in the journals, cited in footnotes, changing nothing. Here is what the Roman concrete discovery actually implies. If Roman engineers 2,000 years ago are producing a marine concrete that outperforms the best material modern engineering can manufacture, then the conventional picture of ancient technology as primitive and pre-scientific is not just incomplete, it is wrong. And if it is wrong about something as fundamental and as physically measurably as concrete strength, then the question of what else it is wrong about becomes very uncomfortable very quickly. The concrete is a proxy, it is not the story. It is the first sentence of a much longer story. The Romans did not accidentally stumble into their concrete formula. The production of opus cementicum was consistent and controlled, across centuries, across the entire geographical spread of Roman construction, from Britain to the Middle East. The same formula, the same techniques, the same results. The specific volcanic ash pozzolana from the region around Pozzuolo near Naples was quarried, transported, and used deliberately. The mixing ratios were consistent. The construction techniques were standardized. This was not lucky empirical fumbling. This was systematic applied materials engineering, practiced at industrial scale across a civilization spanning the known world. Industrial scale. That phrase matters. Not one engineer, not one city, not one lucky harbor. The same formula applied consistently from the coast of Britain to the shores of the Black Sea. Controlled, reproducible, reliable. This is systems-level engineering, not craft, not accident. Systems. And the knowledge was not confined to concrete. Roman lead pipe systems supplied pressurized water to cities of 1 million people at a time when most of the world had no comparable infrastructure. The engineering precision required to maintain water pressure across an urban distribution network of that scale is not primitive. Roman glassmaking produced colors and optical qualities that modern manufacturers spent the 20th century trying to recreate. Colors achieved without modern chemical knowledge. Optical clarity achieved without modern optical theory. Empirical mastery reaching results that theoretical science had to work hard to catch up to. Roman surgical instrumentrico from archaeological sites, so similar to instruments still in use in modern operating theaters, that the comparison has mathematical historians visibly uncomfortable, not inspired by, not ancestral to. Similar enough that the functionalities essentially identical, 2,000 years apart. Roman road construction technique was spread surfaces so geometrically precise and so well drained, that many Roman roads remained in use as primary transport routes for over 1,000 years after Rome fell. 1,000 years have continued use after the civilization that built them collapsed. Each of these achievements, individually, can be explained away. Skilled empirical craftsmen, working within their limitations. Impressive, but not evidence of anything being and what a sophisticated pre-industrial civilization might achieve individually. The word is doing an enormous amount of work. Together, they form a picture that the conventional model of ancient technological capability cannot fully contain. A civilization operating at a level of practical, technical mastery that we have systematically underestimated, because it does not fit the narrative of technology moving in a straight line from primitive, or against modern sophistication. The straight line narrative was always wrong. Technology does not move from primitive to sophisticated in a continuous upward arc. It rises, it falls, it is lost, it is rediscovered. And sometimes what is rediscovered is less good than what was lost. That is the story of Roman concrete. We lost it, not gradually. Not through the slow replacement of an inferior technique be a better one. Not through deliberate choice or rational engineering decision. We lost the knowledge of how to make Roman concrete, because the civilization that possessed it collapsed. When the institutional structures that maintained and transmitted technical knowledge across generations were destroyed by that collapse, the knowledge went with them. Not deliberately destroyed, not burned or banned, just not transmitted. The chain broke, and what was in the chain fell into silence. The recipe for a concrete that improves with age, that withstands seawater indefinitely, that strengthens over centuries of marine exposure, was not written into texts that survived. It existed in the hands and the practices of Roman engineers. When those engineers were gone, it was gone with them. What replaced it was Portland cement, a material that is, in several important and measurable respects, inferior to what the Romans had already mastered. And we have been building with it, watching it degrade, replacing it, and building again, for 2 centuries, because we lost the better solution 1,500 years ago, and only recently rediscovered that it had ever existed. For most of the modern era, we were not even aware of what we had lost. We were building with Portland cement and accepting its limitations as inevitable, not knowing that a civilization 500 years ago had already found a better way. The Berkeley research team and others working in the same field have made significant progress. They have identified the role of the volcanic ash. They have characterized the Tobermorite crystal formation process. They have published the chemical analysis in peer-reviewed journals. The chemistry is understood. In broad terms, they have proposed formulations of modern concrete that attempt to replicate the Roman formula using similar volcanic materials. The chemistry has been analyzed, the formula has been attempted, but a complete working replication, one that matches the 2,000-year performance record of the original, has not yet been achieved. The chemistry is understood in broad terms, but the specific variables that produce the best performing and examples are still not fully controlled. The knowledge that Roman engineers possessed empirically through generations of practice and refinement has not yet been fully recovered through modern analytical chemistry, and there is a deeper problem research has not yet solved. Even if the chemistry is perfectly replicated, the 2,000-year performance record of the original cannot be replicated in a laboratory. The crystalline reinforcement that makes the best surviving Roman concrete so impressive is the product of 2,000 years of chemical interaction with seawater. 2,000 years that modern materials cannot compress into a testing timeline. We know the Roman concrete works because we can see the evidence in harbors that are still standing. We cannot yet prove that a modern replica will work the same way, because we cannot wait 1,000 years to find out. What we can say with confidence, Roman engineers possessed and practiced a materials technology that the most sophisticated modern construction industry has not yet been able to fully recreate, a technology developed systematically, refined over centuries, deployed at continental scale, and then lost so completely that for most of modern history did not even know we had lost it. The harbor at Caesarea Maritima, built by Herod the Great using Roman concrete techniques around 20 BC, has been underwater for 2,000 years. The marine structures are still there, still identifiable, still structurally coherent, still being studied by marine archaeologists who will keep finding the material in better condition than they expect, better condition than expected. That phrase keeps appearing in the reports of researchers studying ancient Roman marine structures, not barely surviving, not marginally intact, better than expected. After 2,000 years, every analysis finds the same thing. The material is performed exactly as designed. Every time someone builds a modern seawall and watches it begin to crack within a decade, the Romans have already answered the question of how to do it better. The answer is available, embedded in every ancient harbor still standing along the Mediterranean coast. We just have not been listening closely enough. There is a particular kind of iron in building an inferior product with complete confidence, while the superior product sits at the bottom of every Mediterranean harbor, available for study, measurably better, structurally intact, and not being replicated, because we have decided the ancient world did not understand what we understand. What we decided, without examining the evidence, was that the ancient world could not have possessed knowledge superior to ours. That assumption shaped what we looked for, what we tested, what we accepted, and it led us to pour an inferior concrete for 200 years, while the superior ancient formulated in plain sight at the bottom of the sea. Plain sight, that phrase belongs in the first sentence of this story, because that is literally where the evidence was, not buried, not hidden, not locked in archives. At the bottom of harbors, along coastlines anyone could visit. Available for study by anyone willing to look. For nearly 2,000 years, the path forward is clear. Volcanic ash, pozzolano, or similar materials, the same principle Romans discovered empirically, now being understood theoretically. Modern construction is beginning to incorporate Roman formulas lessons into new formulations of more durable, more sustainable, longer-lasting concrete, beginning after 200 years of unnecessary delay. The greatest engineering secrets in history were not waiting to be discovered. They were waiting to be remembered. That distinction matters. Discovery implies are moving towards something new. Remembering implies are moving back towards something lost. The Roman concrete story is a story of remembering, of recovering, of admitting that the past knew something we forgot. Roman engineers, working 2,000 years ago, without electron microscopes, without molecular chemistry, without modern materials science, understood something that the modern construction industry has only recently and only partially recovered. That is not a comfortable fact for a civilization that considers itself more advanced than everything that came before. We assume we are more advanced than everything that came before. The Roman concrete says otherwise, not in every domain, not even in most. But in this one specific domain, building structures that survive indefinitely in marine environments, the Romans were ahead of us, and we lost the advantage he had given us. For 1,500 years, For more ancient, mysterious, and hidden histories, stories of what human beings were capable of long before we gave them credit, subscribe and keep exploring, because the greatest engineering secrets in history were not waiting to be discovered. They were waiting to be remembered. Until next time, stay curious.